Well, hello, welcome back to another episode of Language Hacking. And we are starting a series on our parser again, starting over. If you saw the last video, you'll know that I have failed to make a parser using a parser generator and a parsing expression grammar, and decided that it was too slow for our purposes and what I'm trying to build with Natalie, and decided to scrap it and start over. And in the last video, you saw that I had written a lexer that is going to tokenize the input. And so tonight, I want to start the very, very beginning of our parser code that takes those tokens and turns it into an abstract syntax tree. And you'll get to see that in a little bit. But first, I wanted to go over how Natalie compiles and how it works. And some people are no doubt confused why I'm writing a parser, because Natalie already obviously parses code and compiles code into C++, and all that works. So how is it working if we don't have a parser? And the answer is that the way we bootstrap the runtime, the way we compile code is that we run everything through MRI first, Matz's Ruby interpreter, not our Ruby, the standard Ruby interpreter. And our compiler is written in that, and then we turn that into C++. And so I wanted to go over that a little bit with you before I get started. So if you don't care about this part, feel free to skip it, but I thought I'd at least explain. Let's see, how am I going to explain this? If I show you the compiler, this is the compiler itself, compiler.rb, the sort of top level API of it, the top level class that does the work. And it delegates work to these individual passes. Pass 1 transforms the Ruby AST that we get from a Ruby gem called Ruby Parser gem file. We have a right here. We use this gem that we did not write. I did not write this. It's a wonderful gem, and it works great for parsing Ruby. So we take the AST that gem gives us, transform it into something that is still an AST, but it more closely resembles C code or C++ code. Really C code, because it's not really doing much other than some function calls and while loops and in general C stuff. And then pass 2 does, this is a really small pass, only 166 lines of code, does some variable, it determines the scope of variables. Same thing for pass 3. It takes what pass 2 did and figures out how we're going to set and retrieve variables. So pass 2 and 3 could probably be combined, but it was easier to write them as separate passes. And the pass 4 actually takes this this final AST that we've massaged through the different passes and turns it into code that is C++ string, an actual string of C++ code. And so throughout this, you'll see code that is transforming the AST into actual C code. And we write that to a file, and then we tell GCC or clang, whichever one you have on your system, to compile that into an executable. And so that works really great. And this has allowed us to build Natalie for the past year without worrying about a lot of things. Simplified the whole process. So I'm at the point though where I want to be able to do just-in-time compilation, or more specifically, to be able to compile at runtime, which will allow us to do some interesting things with the language that we're hitting a wall, and we can't do that quite yet. For instance, we can only have require at the top level of a file. We cannot dynamically require code in a Ruby file. And so we can't say if this condition is true, then require this other file. We just can't do that because we have to do it all ahead of time. We have to ahead of time compile everything. So we just disallow that entirely. We also cannot evaluate a string of Ruby code because that would require us to parse and compile at runtime. And by the time we get the Ruby that we've parsed and we compile it to C++, our parser and our compiler are way in the past. They're not available to us because they're written in Ruby that we run through MRI, Matz's Ruby interpreter, not our Ruby interpreter, Matz's Ruby interpreter, the real Ruby. Those things, the parser and the compiler, are only available when we're in the real Ruby, not Natalie. And you say, well, isn't Natalie a Ruby compiler? Why can't you just compile the Ruby? Why can't you bootstrap it, right? Use MRI to compile the Ruby to Natalie, and then use Natalie to compile the Ruby from the compiler. Yes, we could almost do that. We're really close to being able to do that. However, we come back to this gem, this Ruby parser gem, which we did not write. It has a C extension. It uses a lot of Ruby internal stuff that I could learn. I'm not interested in learning at this point. And that was my first attempt, actually, was to try to get the Ruby parser gem and the sexp processor, which these two things go together, to get those two things to compile with Natalie. And I was getting closer, but I wasn't quite there. And so I kind of abandoned that project. And so that's what you saw me working on the second attempt at a parser, which was to use a parsing expression grammar. And in the last video, I told you about how I failed at that and have given up on that because the speed just wasn't there and I didn't want to keep going down that road. So here we are, attempt 3 at getting a Ruby parser that we can run in C++ in our own runtime. And so we're going to be writing it. And we've already written the lexer, which turns the string of Ruby into individual tokens, identifiers for variables, numbers, strings, the little square brackets around arrays, commas, all the operators, all those things get tokenized in individual tokens, and they have a type. And here is the type here. These are all the types of tokens that we currently support. And this lexer probably isn't complete. In fact, I know it's not complete. There is a lot of work to be done on the lexer, but it is close enough that I believe we can start working on the parser, which will take the flat sequence of tokens and turn it into a tree structure that then we can feed to our compiler. And that's that. So where do we start? We already have the parser test, and I have this skipped right now because none of these tests actually pass. But what if I turned off the skip and what if I do this? If I substitute it space quote with XIT quote, and that will skip every test. And just to make sure, test Natalie parser test, we want it to say 0 tests have run, all of them are skipped. And so now let's just see if we can get it to parse a number. We'll come back to the empty program, but if we can parse a number, we don't do floats yet, so we'll just skip that one. If we can parse, let's change this to, I don't know, 1, 2, 3, 4 or something, just to make it a little more interesting. I'm having trouble typing right now. So if we could parse these two things into something that looks like this. Now this S parens thing, that is just a sexp. Make sure I pronounce that properly, which is a subclass of array, and it walks and talks and quacks like an array. So for all intents and purposes, our parser can, for now, return an array that has a block symbol first, and then another array inside of it with a lit symbol and the actual value like that. Now, our parser does, we probably don't want the tree structure internally to be all of these arrays. There's going to be a bit of overhead in creating these. We only need to create these for the tests so that we can test that our parser is doing what it should be doing. Internally, the tree structure is going to be some structs and different type of struct that's subclassed for each node type, I believe. So, so in this video, I'm going to try to get just these 2 lines of code working. And if I can get that far tonight, I will be satisfied and happy, and we'll call it a night. So, where to start? I mean, we have a parser value CPP, and this let's actually go to the header. This is just the interface to the runtime object, the parser object in Ruby itself. But I think internally we want to do something like we did with Elixir, where we have just this internal struct that does the work, and then that parser value can just talk to that. So I'm going to save this as parser.hpp, and we'll change this to parser, and not actually sure. I guess that would be input. Yeah, that's fine. We'll say this is code. And don't care about that for now. And I'm just going to delete pretty much everything. Yeah, so let's just delete everything, and this will be coscar m code. And we want, let's open our parser value CPP, which has a parse method, and currently we're returning nil object because that's all the code that we deleted in the last video. But if we, what are we going to do? Parser and we pass in the code. We'll make sure that it's a string, and actually let's do this. Assert type env value type string and string. Make sure that we're good boys and do the right thing. And we'll turn this into a cstir. Probably need to actually import that. And how did I do the Elixir? Did this? ToRuby is a method on each token. Okay, go down some more. Down, 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 down. So I have a tokens method on there. So actually just gonna kind of copy this and put it over here. And we're going to say this returns a node pointer. And we'll call this tree. And it's going to return something. And so we need, and what did we do over Elixir? I want to kind of be similar in how I format this. So this is going to be a node. having trouble seeing what I did wrong here. Well, we know that it's going to have a line and a column. We know this. Not sure what the constructor is going to do just yet. And I have to figure out why this is. So why did you expect a... Why did you expect that? Why? Why? What if we were just return a new node? Does that make you happy? Okay, I'm just going to run make here because I'm getting a little confused. Okay. Apparently just need to restart. Parser HBP. And now it's okay. That was weird, right? It was telling me some weird errors, so that restarting helped fix that up. So yeah, these aren't usable. So we'll just say line returns m line, and column returns m column. So now are you happy with that? Okay, cool. So that returns a parser node. How am I going to do this? Just looking at some code for inspiration here. I think that I want to do a struct of, let's see, a block node. Let's go to the parser test. We're going to need a node for block and for literal. So what if we do this? And the block node takes what does it take? Does it take a vector? Well, let's think about what it has first. So it's going to have a vector of nodes, pointers, called inNodes. Yeah, like that. And let's not even create a constructor for it, but let's create a, let's see, void add node m nodes push node, and we'll need a getter vector node nodes turn Do I even want to be able to get that? Probably not. That's probably pretty dangerous. I'm gonna try that for now. Okay. And then we need a literal. Is it going to be a literal? Yeah, a literal. Literal node. And it's going to have a constructor. Literal node. And it's going to take a value. Okay, so do we have enough? Let's just leave this off for now, and let's make a toRuby method that let's see, auto array equals new array value, and we're going to return that array, and we're going to do and going to give it a symbol, intern env block. And then we're going to loop over the nodes in M nodes and append to the array. Push node. Why are you unhappy? Wait, why are you unhappy? No matching member function. Really? Push value. Oh, right. Node to Ruby. Pass the environment. And this is going to have to be a virtual method. Virtual. And I guess we can just return nil object by default. And this will be virtual override. Come on. So now this one has a toRuby method, and I'm just going to delete that. I don't even want that on there. And then our literal node needs one as well. And it's going to look very similar, a little bit different. So for this one, it's going to be a lit followed by a, just return the M value. And we can just return this, actually. We don't need to do all this stuff. Okay, let's look through this real quick. So what we've done, we've created a parser, and inside of that namespace we have a node object, which all it really does by default is store its line and column number, which currently we don't even have a way of recording, but that's okay for now. We'll come back to that. We have a block node, which is going to be a series of expressions, or a series of expressions. So the top level program is a block, not to be confused with a Ruby block. It's just a block of expressions, a list, several expressions. I don't even know. I'm just keep saying the same thing over and over again. Maybe it'll make sense. Each one of these has a toRuby method that turns it into a Ruby array, so we can do some testing on it. And we have a literal node that just keeps track of a Ruby value. And we have this tree structure. So what if we do this and we return the tree, and this should, interesting. how is that going to work? Parser value CPP. So if we return parser tree to Ruby, parser tree. I mean, the skeleton is there. There's no meat to it, but the skeleton is there. And so this test should fail for the right reason. And what I mean by that is that we want to start with a failing red test. And we want it to have the infrastructure there so that it's failing for the right reason. We don't want a seg fault or something. Like this is perfect. We're returning nil. And so now we can see that our plumbing is there to do what we want to do. We just don't have the actual business logic for converting our string of tokens, which we haven't even gotten yet, into an AST tree. So let's work on that. And I suppose first, let me just remind myself how this works. Let's go down here. Oh my, it's long. Really? Oh, it's at the top, right. So you just construct a Lexer object with the input string, and then you call tokens on it, and it returns a vector of tokens. So I guess we want to do tokens equals Lexer and mcode. Use of undeclared identifier Lexer. Yep. And dot tokens. We can just throw away that object. And let's do this. Tokens, just so we can kind of see, because tokens 0 has a to Ruby. Is that right? How does this work? We get the tokens here. Oh, I see. We're looping over the vector like so. Right. So we want this to be a new block node, because that is our first item here. So we want the top level to be a block node. And a block node what am I missing here? It's not a pointer, that's right. And we'll just do inspect. And I need to pass in the environment here. Okay, what are you complaining about? There we go. Okay. I kind of want to see what the tokens look like for each of those tests. Let's just do one test for now. Let's just do the number 1 all by itself. Redefinition of lexer. Really? Well, that's probably because we didn't put a pragma once, and we didn't put it here, and we didn't put it in the lexer. Let's try that. Okay, so we got this one token here. Cool. And let me remind myself what methods the token has. It has a type method that returns a type. Cool. Okay. So I guess we want to do this. We want to say for auto token in tokens. And I have to dereference this probably. And what is the simplest possible thing that can work? All we care about right now are integers. So what if we did switch on the token type, and we say case token type integer. I'd have to do lexer token type integer. Default. We're just going to skip it. Break. What is wrong with my indentation? That's weird. Now, why don't you like this? Expression result unused. That's fine. So I want to say tree add node. A literal node. And the literal nodes is the token dot literal. Just gonna turn it into a thing. And this, why don't you like literal node? Why don't you like it? Expression result unused. Expression result unused. Lexer does not refer to a value. Oh, let's do, yeah, let's add enough colons for that to work. No matching constructor for initial session. Well, returns, you pass in a value. Do I have to mark that? No, I don't have to mark the constructor as virtual, right? No? No. Like over here, I have integer value. Yeah, that should just work. Why doesn't that just work? New literal node. No matching constructor for initialization of parser literal node. Okay, let's see if I get a better error over here. No matching function call. Candidate. Yes. No non-conversion of argument 1 from const car. Oh, right. Because... Now, wait a second. I thought we were storing the integer somewhere. Oh, we are. Integer. Aha. So not literal. We'll do integer. And what it's a nat int t, so we need to make it a new integer value, env, and this. And no break. Does that make our test pass? It does make our test pass. Beautiful. Let's see if we can get this one to pass. Should just work, I believe. Yay! Haha! It works. I shouldn't be surprised when my code works, but I almost always am. I never have a lot of faith in myself, but sometimes things work out. Okay, so this isn't a bad, let's just reevaluate this a little bit. This isn't a bad hierarchy, I think. Honestly, I'm not even sure that this has to be virtual. Yeah, I think it does, because later we're going to have things that reference other nodes, and they're not going to know what kind of node it is. So that needs to be virtual. Okay. Well, you know, that went pretty well, and I wonder if there's something else in this parser. We don't want to do floats yet because our tokenizer doesn't tokenize floats. I'll work on that later. But I wonder if there's something simple. Well, we could probably do this empty program. Let's just see what happens when we try to parse an empty program. Do we get an empty block? I accidentally typed something, so got some weird output. But it says it passed. Now, how did that work? It kind of accidentally worked, right? Because of this default. I'm going to put unreachable here and see what happens. It could just be that there is no token. So yeah, I guess there's nothing happening in here because we don't have any tokens, which makes sense. So we got 2 tests passing. What else can we get passing really easily? Possibly strings. We could possibly work on strings. Probably no quoted ones. Nothing with escape characters. But these 4 should work. I think we can get that working. So let's see a failing test. Always start with a failing test. Panic unreachable. Okay. So we get to do another branch in our switch statement. This is going to be a string. And we're going to add a node, another literal node. And it's going to be a string value. And we're going to return the literal and see what happens. Oh, it's not a literal node, it's a string node. So we need a new node type. And we'll just put this here like so. String node. It has a value. Same. This is going to be a stir. And let's see if that fixes it. It does. Woo-wee! Well, I am counting this as a successful evening. We have the very beginning of a recursive descent parser that is able to just parse a couple literal values, integers and strings. So in the next video, let's work on some operator stuff, possibly. or maybe method calls. I'm not sure which would be easier. Maybe method calls. But yeah, we'll work on something a little more advanced, and things will start to get exciting. So thanks for hanging out with me tonight. And as always, I love your advice and your words of encouragement and anything you can throw at me to help me stay on this project. Like I said, my goal is to work on this every evening for the month of December. And if I can, if time allows and family obligations allow, I will make a video about my progress. And want to share that with you. And if I fail again, then I get to share that failure with the world. And it's a very humbling experience, and it's good for me sometimes. But hopefully we won't fail. Hopefully we'll make good progress and write the parser that Natalie deserves. And so I thank you for hanging out with me, and I hope to see you in the next video. Bye.